we begin with ulum kita al-Fatihah. Okay, so what do you know? Have you ever heard the major loss in a pipe before, everyone? What do you know of parameter that involve of the losses in the pipe? I believe maybe some of you have learned before about the major loss. What do you think of major loss happen inside the pipe system? What do you think?
Excuse me, doctor. When the pipe is long, the more
Okay.
long the pipe, the more major we have, the major loss.
The more what type of loss? The more
Energy
the
loss
energy loss due to
due to the long length of the pipe.
Due
okay.
to friction.
If that pipe is a smooth pipe, do you think will have any losses?
No, doctor. Yes, because of the friction.
Okay, yes. Someone just answer correctly. Basically, the major losses come from the friction along the pipe. Okay, the longer the pipe will have the longer friction because the friction directly proportional to the length. Okay, later on I'm going to explain to you. Okay, so here major losses. So for today's session, I'm going to explore two type of losses, which are major and minor losses. So now we focus on a pipe only. Okay, we are not focusing on the parallel channel or any kind of geometry. So for this geometry, we consider a circular geometry, that is a pipe. Okay, so for the pipe, of course, we have the diameter. All right, so most calculated quantity in the pipe flow is the heat loss. All right, normally we measure the loss using the heat loss. So by using the heat loss, allow the pressure change to be found. So this application of the heat loss, we can use to select the pump type. Alright, different industry will produce different pump. So for our application, we need to select what type of pump that really match to our specification based on the heat loss. And derive from the energy equation. Okay, this one here. Derive from the energy equation. I believe you know the energy equation before. Okay, so this is the heat loss, which is delta P, okay, over, okay, so over gamma. Okay, so why? Let me explain to you clearly. Alright, so what's the energy equation? Okay, let me call one by one. Okay, let me call from section. Okay, I would like to call Abdullah Ahmad Abu Drabika. Are you there? From section 1. Okay, I think it's not coming. Okay, I call Amin Alariji. Are you there? Okay, no. Muhammad Hasibul Hasan Imran. Are you there? Okay, no. Umar Ibrahim Muhammad Alaribi. Are you there? If you hear me, please unmute your microphone and answer me. Okay, not there. Siti Wahda Aulia. Are you there? Okay. So we proceed to section 2. Andika Dwi Rachmat. Are you there? Muhammad Ashraf bin Muhammad Masri from section 2. Are you there, Ashraf? Okay. Okay. Nordiana Muhammad Azhar. Are you there? Okay.
Sorry, I was there. I was here, doctor.
Okay, Andika. Your name Andika Dwi Rachmat, is it?
Correct.
Okay, Andika. I would like to ask you, can you state the energy equation considering the heat loss? Okay, what's the energy equation? Do you not remember the last class we learned about energy equation? Okay, let me describe to you. We have the long pipe. Okay, let's say this is the pipe system. A long pipe. Okay. And then we have the flow. Inlets and outlets. How do we state the energy equation? Can you just state the general energy equation? Andika?
Is it F L over D?
No.
Wait. I forgot it.
Okay. Anyone would like to help will get 10 points. Would like to try, anyone?
Can I try, doctor?
Yes,
Okay.
doctor.
Yusuf, are you? Okay, Yusuf, are you there?
Yes, I am here.
Okay, Yusuf, section.
Section 1.
Okay, Yusuf, your first name Yusuf, is it?
Yes.
Okay, Yusuf Amir. Okay,
Yes.
what's the correct energy equation?
B1 over rho G plus V1 square
Okay,
over
V1,
2G.
V1
Okay.
over
Square.
rho G
Yes.
plus
B1
D
B.
B.
Yes. No. P.
Oh, P. Portugal. P
Over rho G.
over rho G.
Sorry, doctor. V over 2G.
Okay. V over 2G. Okay, now it's okay. V over 2G.
Yes.
Wait ya. Okay, V over 2G.
Yes.
And then
Plus Z1.
Z1
Yes. Equal V square 2. V2 square.
So this is one lah.
Yes.
And repeat lah.
Yes. And at the end plus HL.
Can I replace rho G with gamma? Is it okay? Or is it wrong?
Yes, yeah. Yeah, okay, okay.
Okay. Plus Z2
Yes,
and
plus
then
HL.
yes, correct. Okay. Thank you very much. Yusuf Amar, you from section, you got 10 points. Okay, thank you, Yusuf, for giving the correct answer. Okay, so based on this one, how to form this one? Okay, basically you can see here we have Z1 and Z2 the same. Cancel, cancel. Okay, so we know that the pressure outlet P. Okay, sorry. Okay, this is P2, this is P1. Okay, so P2 and P1 they have the value. Okay, this one is a gamma. We can replace this one. Okay, and then we can look at the velocity. Okay, assume this is constant velocity. Okay, the velocity is the same. Alright, so we can cancel velocity out, velocity out. So what do we have now? We have P. Okay, this one move to the other side. So P1 minus P2 over gamma equal to heat loss. Okay, so this one basically lead to the delta P over gamma equal to heat loss. Okay, simple like that. Okay, this is when we consider as the horizontal. When we have the inclination, what do you consider? For example, this is the pipe section, incline a little bit. Okay, we have Z1 and Z2. So definitely, okay, the energy equation will be V1 squared over 2G plus P1 over gamma plus Z1 equal to V2 squared over 2G plus P2 over gamma plus Z2 plus heat loss. Okay, so when we have the height, so let's put this way, this is our reference point and this is H. Okay, so the Z2, the V1 we can cancel, assume it is okay, assume the cross-sectional area is the same by following the continuity equation. Q1 equal to Q2. Okay, area V1, area V2. When the area 1 and area 2 is the same, so velocity at point 1 and velocity at point 2 is the same. That is why we cancel out velocity 1 and velocity 2 because of the same cross-sectional area. Remember that. Okay, and then we have the height here. Okay, so from here, okay, we can shift out. So this one we move this side to the other. So P1 minus P2 over gamma plus ZY minus Z2 over, okay, Z1, Z2 over gamma. Okay, that's Z. Sorry, heat loss. Okay, so heat loss basically, alright, this one delta P over gamma Z1. Okay, Z1 minus Z2. So this is 0, this is H, so negative H. Okay, so you can see that the heat loss directly depend on the pressure drop and the height as well. Okay, so the heat loss from the wall shear in the developed flow is related to the friction factor. Okay, this is the pipe. Okay, let me use other color. This is the pipe. Okay, the same cross-sectional area. You can see that we have the wall shear due to the friction and the viscosity of the water. This friction will develop the friction factor. Okay, we have the friction here. So, based on what we learned from the previous class, the friction we can use to convert from the friction into the normalized friction factor. Do you still remember what I mean by normalized, everyone?
Dimensionless.
Okay. Yes, perfect. Dimensionless. That is why friction factor is dimensionless, no unit. So from here, okay, from here, friction factor can be related to the function of rho, the density, the viscosity, the velocity, the diameter, and the roughness height. Okay, so this equation has been discovered by Darcy-Weisbach equation. Okay, this person named Darcy-Weisbach discovered this kind of dimensionless parameter and named by his name. Okay, so friction factor depend on the velocity. So you know that velocity is related to Reynolds number. What's the Reynolds number? Reynolds number is rho v d over mu. You can see we have velocity. So friction factor depend on, you can see friction factor depend on velocity. You can see we have the density. We have density. You can see we have viscosity. Viscosity. And we have the diameter. Okay, we have the diameter. So you can see rho mu Vd is a Reynolds number. And this is the roughness height. Okay, this is the pipe. And we have the roughness. Okay, this here, from here we call as the E. Okay. Okay, so far you guys understand what is mean by F, rho U, okay, Vd and E. Okay, so how to calculate, how to get the friction factor? So this person, Darcy-Weisbach equation, developed the Moody chart. Okay, this is we call a Moody chart. Inside the Moody chart, we have the primary axis and secondary axis. The primary axis refer to the friction factor. Okay, the highest number of friction factor will have energy drop. Okay, and this is the Reynolds number. You can see the x-axis is the Reynolds number. So friction factor can be found from the Reynolds number and with the help of relative roughness. How to get the relative roughness? You can see this roughness, as I mentioned before, this E is a roughness. Okay, in engineering field, we are not consider any value. We need it to be dimensionless. That is why this E, we have to divide by diameter. We call this as a relative roughness. You can see E is the meter. Diameter is a meter. So meter divided with meter is dimensionless. Okay. So this E over D is relative roughness. You can see in the Moody chart. Okay. As you can see, relative roughness E over D. Certain pipe or certain material will have different kind of E. For example, like concrete. Okay, we have the E equal to 0.323 mm. For example, like wood, when the pipe is made by wood, the roughness here measured in millimeter, it is 0.3. And same goes to the rest of this material. Alright, rough iron 0.046. millimeter. Alright, when you use in the equation, please use meter as the SI unit. Okay, I hope you are pretty clear about this. Okay, this Moody chart is very useful to get the friction factor. Okay, based on the Reynolds number. So this is a little bit of the explanation of the Moody chart. Okay, so from here, Moody diagram is plotted based on the experimental data. Remember that previously, when we have the dimensional correlation, we can form the experiment. So the Darcy-Webash developed an experiment to investigate the correlation of friction factor with the density, with the velocity, all those kind of parameter. So that kind of chart we call as a Moody chart. So Moody chart is developed based on the experimental data relating to the friction factor and Reynolds number. So this is Moody chart, this is friction factor and Reynolds number, and here is the relative roughness. Okay, for fully developed pipe flow over the range of wall roughness, okay, this value can be found from the figure. All right, fully developed, you can see. Okay, this is the region of completely turbulent region. You can see it's a horizontal line. This is the laminar flow. All right, when the flow is considered as a laminar flow, you can directly pick the value using this line. This is critical zone and this is transition zone. Okay, let me explain to you. You can see this Reynolds number from the left to the right is increasing number. Okay, based on the actual flow, we have, for example, this flow inside the pipe. Okay, this flow is laminar flow, initial flow, right? So after a certain time, the flow start to transition, to transit from the laminar flow to the turbulent flow. Okay, this region basically is laminar, this is transition, and this is turbulent. Okay, so that is why you can see it start from the left to the right. The left, you can see this is laminar, refer to the low Reynolds number, and this one, a transition zone, refer to this number, and completely turbulent regime, refer to this number. Okay, so this one, for a smaller relative roughness, okay, that means the E over D, yeah? For the smaller relative roughness, that means this E is very small and D is very high, is large. As Reynolds number decreases, friction factor increase. Okay, so that means low Reynolds number, the friction factor increase. Is it true? You can see. Okay, this one. For example, let's say we use this one. Okay, low Reynolds number, this one. You can see when we go to the from the right to the left, the friction factor increasing. Okay, it is true. For Reynolds number less than 2000, it is considered as a critical zone. Remember that the critical Reynolds number for the laminar, okay, a couple the turbulent flow to the laminar and may represent the oscillating flow. This is a chaotic flow, oscillating flow like this. Okay, oscillating flow. So assume new parts. As the pipe get older, corrosion occurs. Okay, occurs changing both the roughness and the pipe diameter. Right. So that means when the pipe gets older, the corrosion will happen, and then it will corrode inside the internal pipe. So the diameter will change. the cross sectional will change. So it will change the friction factor. Okay, so basically how to solve when we involve with the major losses. Okay, so inside the pipe we have major losses that can be categorized into 3 problems. Okay. Okay. By the way, for this one, this is the general formula. Head loss when the head loss involve the friction factor. Okay. So you can see here. Yeah, it's not in. Yeah. Okay, this one. Based on this Darcy-Weierach equation, we can form this formula. Head loss is equal to friction factor L, okay, over d V squared over 2G. I hope you can remember this. Basically, it is the same like this. Okay. The head loss is the friction factor multiplied with L over D, V squared over 2G. This is the calculation to get the head loss related to the major losses. Where's the major losses? This one. This friction is the major loss. Okay. So basically, there are 3 types of problem for the major losses developed inside the turbulent flow. Okay. The first one is category A. Okay, let me put this way. Category knowns. This is unknown. This is what we need to solve. And this is known. It is given or given in the question. So we have 3 category or 3 problem. Problem number 1, category number 1, category number 2 and 3. The first, the question asks to find the head loss. Alright, so it is given Q, the flow rate, the diameter, the roughness height, and the velocity. The second problem is quite hard. They need you to find the flow rate of the water, given that it is given diameter, is given the roughness height, the velocity, and the head loss. And the final one to ask you to find this one, diameter of the pipe. Normally, for the type number 3, the category 3 is the hardest. Okay, the hardest one, because this is more on the design. Okay, you need to design, you need to propose what's the best diameter. Okay, so in order to get D, you must know Q, you must know E, you must know velocity and the head loss. The easiest way is this, the category number 1. Okay, so in order to calculate this, we have 2 methods. The first, we can use the Moody diagram. Okay, the second one, we can use the equation. Okay, we have this equation with the condition given. Okay, for example, the question asks, find the head loss by using this equation. Okay, you need to substitute the value, all the value here, and you will get the final answer. Okay, same goes to number 2 and 3. You need to find Q or D. Just substitute here Q and D, you will find the final answer. Okay, this is based on the equation. Sometimes when the question asks specifically, please use the Moody diagram. So by hook or by crook, you need to use this Moody diagram to find the friction factor. From the friction factor, you can find the head loss. Okay. So let's try one example. Okay. So water at 20 degrees Celsius is transported for, okay, let's say this is the transported for, this is the length, right? The length is 450 meter in 38 millimeter. This is diameter. Rough iron, this is material. Horizontal pipe, so that means the Z1 and Z2 the same. With the flow rate, okay, so let's say L equal to, let this out. Okay, the pipe is very long from here to here. Okay, the L is 450 meter and the diameter here is 0.038 meter. This is the diameter. Okay, 1, 2, 3, 0.038. Okay, confirm. And the diameter here is 0.038 meter. And material is rough iron. So based on this, we can get the E. What is our E? Okay, our E here from the table or from the Moody diagram, you can see here. Where is the rough iron? This is the rough iron. And please choose this one. Your unit is millimeter. Use the metric unit. Alright. So it is 0.046 millimeter. Alright. So 0.046 millimeter. Alright. And the flow rate is, this is, flow rate is volume flow rate, Q. 2.75 liter per second. First question, calculate the heat loss. So this is category under category number 1. Okay, over the pressure drop and the pressure drop. Okay, so the question asks the pressure drop, the delta P. Okay, the delta P over the 450. So you need to divide by this number. Using the Moody diagram, you can see two methods using the Moody diagram and alternate method. So alternate method using the equation, simple. So the first question, we need to find the, okay, we need to find the friction factor. We start with the Moody diagram. So how to find the friction factor? Look at from our diagram. Okay, in order to get the friction factor, what do we need to involve here? Anyone? In order to get the value of friction factor, what we need to know? Muhammad Alif Najmi bin Johari, are you there? Alif? No. Okay. I give to Aina. Are you there, Aina?
Yes.
Aina? Okay. What do we need to involve when for us to calculate the friction factor?
We need, following the equation, we need density,
Okay.
velocity, diameter.
Okay, why we need those? Okay, based on this.
and
Okay, based on this figure, based on this Moody diagram, in order to get the friction factor, what parameter we need to get extra?
Can I answer, Doctor?
Okay, Aina, I give Aina chances. Okay, what we need to
so
have?
we need to have for finding the friction through the Moody's diagram. Is that the question?
Okay. Okay. I give to Hani. Hani, can you help me? How to get the friction factor?
We need to calculate the relative roughness first, which is
Relative
E over T.
Is it only one relative roughness and we can get straight away the F?
The Reynolds number?
Yes, perfect. Okay, Aina and Hani. Aina from section?
1.
Okay, Aina. Okay, you got 10 point, and Hani Ahmad from section 1.
Yes, doctor.
Okay, HA, is it your first, right?
Yes.
Okay, Hani Ahmad, thank you. Okay, basically, in order to get friction factor, everyone, you must have this one. You can see Reynolds number. You need to have relative roughness. So, what's the formula of Reynolds number? Okay, so in order to get Reynolds number, what Reynolds number involve? Okay, please list out. Okay, like this, yeah. Okay, in order to get the friction, okay, you need to have the Reynolds number, as well as you need to have the relative roughness, right? So Reynolds number, in order to get Reynolds number, what do you need to have? You need to have the velocity, because Reynolds number is directly related to rho v d over mu. Okay, mu, you can see, you can get directly from the table. Considering this temperature, you can get the density, which is 1000. You can get diameter already given, and velocity. Velocity is not given. Okay, so in order to get E over D, you must have the material, which is material rough iron. It is given. The E here is 0.046 millimeter. Now, so what's your plan? You need to get the V. So here, in order to get the V, okay, let's say this is step number 1. Okay, in order to get V, step number 2, I want to get the V. How to get V? From the
Flow rate.
yes, perfect. From the volume flow rate, Q over A. In order to get, what happened here to my, okay. So Q equal to AB. This one I rearrange. Okay, Q. The flow rate is, I think it is given. Is it given? Yes, 2.75 liter per second. So now the flow rate is in liter per second. You need to convert into meter per second. So you need to divide by 1000. So 2.75 liter per second divide with what? Divide with 1000, which is 10 to the power of negative 3. Wait, yeah. Let me close. Okay. This is the unit of meter cube per second over the area. So what's the area? Area of what? Area of this cross-sectional area. So area of the cross-sectional is pi d squared over 4. Okay, so or you can use pi r squared. Okay, for the simplicity. So pi radius. So what's the radius? The radius is divide by 2, this one. So divide by 2 is 0.019 squared. So you calculate using calculator, you will find the answer is 2.43 meter per second. Okay. Wait, yeah. Okay. So after we get the velocity, okay, consider the velocity is constant. So we can get the Reynolds number. So step number 3, Reynolds number, which is, okay, you can use a B. d over nu. Okay, you can use this equation. This is the second version of Reynolds number. This is nu, yeah. This is the viscosity nu. Okay, this is velocity. So velocity, just substitute 2.43. The diameter is 0.038. And the nu here, the viscosity here is 10 to the power of -6. Okay, this one you can get from the table, appendix section, Chengal book, table B1. You can get the table, you can get this nu, the viscosity. Okay, what happened here? Okay, from table B1, appendix section, at temperature 20 degrees Celsius. You can see here, water at 20. Different temperature will give you different viscosity. Okay. So, upon calculating this, you will get the Reynolds number equal to 92,300. Okay, this is definitely turbulent. Okay, because this value more than 2,000. 2,000 is the critical Reynolds number. So after we get this Reynolds number, okay, the E over D is step number 4. You can get the relative roughness E over D, which is 0.046 multiplied with 10 to the power of -3. This is millimeter, yeah, over with diameter, which is 0.038. Okay, you will get the answer here is 0.0012. Okay, based on this value and based on this Reynolds number value, directly, okay, let me use the clear versions of the Moody diagram. Wait, yeah. Let me use another clear versions of Moody diagram. Okay, this one. Okay, this is our Moody diagram. Okay. Okay, it is clear now. So, where is it? Okay. So I hope you can see, okay. Reynolds number 92,300. Where is the Reynolds number? So you can see here. This is 1, 2, 3, 4. Okay. That is here, around here. Let me. This is. Okay, this one. Okay, this is 9. The power of 10, 9 multiplied with 10 to the power of 4. This one, yeah. Around here. Okay. So when doing this, you need to use the ruler lah. Okay. So okay, and then relative roughness 0.0012. This is 002. This is 001. Okay, around here. Okay, now meeting here. Okay. So this is the cross-sectional. This is the intersection. Directly go to the directly go here. Okay, use the ruler, yeah. Okay, this is the friction factor. Okay, when you use a ruler, you can find that the answer is around 0.02. Okay, so
Doctor,
Yes.
is it 10 power of 5 or 10 power of 4?
Which one? 10 to the power of 5. Which one?
The Reynolds number.
This one?
Yeah, it's power of 4, right?
Yeah, power of 4.
You choose down 10 power of 5, right? In the schedule.
Which one? This one?
The one you choose is 10 to the power of 5.
Okay, which one start with 1? Okay, 1 start from where? Okay, this is 1, right?
So,
okay. This is 10 to the power of 5, start from here, right? And before this is 9, right?
okay. Oh, I thought it's stuck. My bad, sorry.
Okay, so do you manage to okay, let me clear about this. This
I understand.
is
And I start counting to left, not to right.
9.23 multiplied with 10 to the power of 4. So this value is 9. So this is 10 to the power of 4. You can see where is 10 to the power of 4?
Yeah, I thought the 9 at the right is belongs to 10 power 5, and the 9 left belongs to 10 power.
Okay, it's okay. So this is 10 to the power of 4. We calculate from here. This is okay. This is 2. This is 1. This is 2. This is 3. This is 4. This is 5, 6, 7, 9. So 9. 9.2. That is why I choose this number straight away. And then the relative roughness around this. So using your ruler, you will get around 0.02. Okay, you must make sure correctly choose here the Reynolds number 9.23 to the power of 4. Okay, so based on this Reynolds number and relative roughness, step number 5, you will get the friction factor. Okay, around 0.023 lah. Okay, this is the accurate one lah. You use the ruler. So based on friction factor, step number. So what we need to do? We can get straight away the head loss. Step number 6, which is head loss, which is friction factor L over D, V squared over 2G. Okay, velocity we have diameter and friction factor. So just substitute 0.023. The length is, you can see, 450 over diameter is 0.038. And then velocity is 2.43 squared over 9.81. Okay, so from here you will get the head loss is 82 meter. Okay, this is the unit of meter. Okay, so after we found the head loss, step number 7, we know that in order to get the pressure drop, okay, you can see our previous equation. Okay, you can see head loss is equal to the pressure drop over gamma. Okay. So based on this, head loss is equal to pressure drop over gamma. Okay. So in order to get the pressure drop, just rearrange delta P equal to head loss multiplied with gamma, specific weight. So delta P is equal to head loss is here 82 multiply with gamma. What's the value of gamma? Okay, gamma is we expand rho G, which is 1000 multiplied with 9.81. So the the pressure drop is 84 Okay, 804.4 kilopascal. Okay, so what can you deduce from this one? Okay, I want to make you very clear on this here. Okay, we have the long pipe. Very long pipe. Okay, let's say the pipe is 450 meter. And this is to the atmospheric condition. So what do you think of this atmospheric condition, pressure? Pressure 2 is equal to 0. So definitely we have the pump. In order to pump this fluid from inlet 1 to outlet. So this pressure at 1 is this value. Okay, in order to move the water from position 1 to position 2, the pump need to pump with the pressure 804.4 kilopascal with the length of 450 with the relative roughness of rough iron. Okay, everyone, do you understand? If the pressure is not enough, is less than this value, what happens? Anyone would like to try? If the pressure at the inlet is less than this value, what happens? Are you guys there? Or sleeping?
Doctor, the flow will not be turbulent.
Okay. Not turbulent? I don't think so.
The water cannot flow.
The water cannot flow. Water unable to achieve the final destination, which is at point number 2. Okay. So in order to let the water inlet what we call arrive at point 2, we need this pressure. Why we need this pressure? Because we have the friction, we have losses, right? We have the major losses. So these losses will require this much of pressure to pump. Okay, everyone, do you understand about this concept?
Yes, doctor.
Okay, thank you very much. Okay, last we use the alternative method. Okay, what's the alternative method? HL equal to, okay, this is our alternative method. So head loss, just substitute the value 1.07. You can see the relative roughness is between. This is the condition here. In order to use this formula, you must obey this condition. Relative roughness between this value and the Reynolds number within this value. So we pass the condition. So we can use directly this equation Q. Q given already, which is 2.75. 2.75 multiplied with 10 to the power of negative 3 bracket here, squared. The length is 450 over gravity 9.81. The diameter is given, which is 0.038. Okay, the power of 5. Okay, this is actually bracket. Ln. Okay, natural log. Relative roughness is given already. Okay, E is 0.046. 0.046 multiplied with 10 to the power of negative 3 over 3.7 multiplied with diameter 0.038 plus 4.62. Velocity is calculated already, which is 2.43. 2.43. The diameter is 0.038 over flow rate Q again 2.78 multiplied with 10 to the power of negative 3. Okay, and then close bracket, the power of 0.9. Okay, close this one. You need to settle inside, and then outside you have to the power of negative 2. Okay, so I hope you understand how to solve this one. This is the basic of mathematics, yeah. When you have the bracket, solve the bracket first. So you need to solve this one. After that, you learn it. After you learn the power of negative 2 and then multiply with this one. And finally, you will get the head loss is 82. Okay. Is it the same? You can see 82. The same that we used before this using the Moody diagram. So directly from this one, the pressure drop delta P is equal to head loss multiply with the gamma, which is 82 multiply with 9810. It is the same answer as this one before, which is 804.4 kilopascal. Okay, so far everyone understand about two methods, the Moody diagram and the alternate method? Everyone?
Yes, Doctor.
Okay, so I think that's all for today. It's very extensive because this one, basically the category 2 is easy, but it takes many steps. Okay, I hope you understand step by step. If you don't understand, please do revision, okay? And focus as well on your test.
Doctor, can you show that?
Okay, yeah. Okay, can you see?
Yes, Doctor. Thank you, Doctor.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Okay, sure, thank you.